Hi, I'm Kanarek, and today I will be talking to you about a variation on a famous unsolved problem in number theory, the Erdős-Straus Conjecture, which was formulated by Paul Erdős and Ernst Strauss in 1948. The conjecture is, for every n greater than or equal to 2, there exist positive integers x, y, and z such that 4 over n equals 1 over x plus 1 over y plus 1 over z. This hasn't been proven, but computer searches have verified it for all n from 2 to 10 to the 17th. There are ways to simplify the problem. For example, if 4 over n can be made from summing two unit fractions, 1 over x plus 1 over y, then it can be expanded to 3, 1 over 2x plus 1 over 2x plus 1 over y. Also, only prime values of n have to be checked, because whenever a solution exists for a given n, one also exists for all multiples of that n. By the distributive property, you can just multiply x, y, and z by the same amount as n. It has also been proven that certain values of n have solutions based on their remainder modulo some number. For example, if n is 2 mod 3, then 4 over 3n plus 2 equals 1 over n plus 1 over n over 3 plus 1/3 plus 1 over n times n over 3 plus 1/3. These are called congruence relations or modular identities. Such relations can only exist for numbers whose remainders are not perfect squares, called quadratic non-residues. Here are some congruence relations that I worked out for values of n which are 7 mod 24, 5 mod 8, 17 mod 24, and 11 mod 24. I've also included an example decomposition for each congruence relation for n equals 1. I won't go through them in detail. While working on this problem, I realized that this talk wasn't going to be for G4G4, but G4G14. So obviously I need to be thinking about a different numerator. What about 14 over n? 14 over n is a very similar problem, but there are some key differences. Unlike for 4 over n, some relatively small values of n can't be decomposed into the sum of 3 unit fractions. I found those with the Python program, and there are 12 of them smaller than 100,000. Just like for 4 over n, I worked out a bunch of congruence relations for different values of n. 0 mod 7, 6 mod 7, 12 mod 14, 10 mod 14, 8 mod 14, and 9 mod 14. I've also written here a list of the 12 values of n less than 100,000 that don't work. You might notice that 2 of the modular identities have a 2 in the numerator. These are still unit fractions because if n is odd, then n plus 1 is even, and if n is even, then the other expression is even. So the denominator will always be even, and you can reduce either one to a unit fraction. Here is a graphic of the first 1,000 values of n with the modular identities color-coded. Red squares are values of n that don't work, and gray squares are for values of n where I haven't yet figured out a modular identity. The congruence relations I've worked out so far cover just over half, 569 out of 1,000. In summary, the Erdős-Straus conjecture is, for every n greater than or equal to 2, there exist positive integers x, y, and z such that 4 over n equals 1 over x plus 1 over y plus 1 over z. It hasn't been proven yet. We can use congruence relations to find solutions for a lot of denominators. The story is different when we change the numerator to 14, because we know of some denominators that don't have solutions. So far, I've managed to find congruent relations for more than half the possible denominators. Thank you so much for listening. I also want to thank Larry Washington at the University of Maryland for all his help. Is there time for any questions?
Yeah, we have time for one question. Do I have time for one question? Okay.
Gabe, how did you become interested in this particular problem?
My favorite area of math is number theory, and it's a number theory problem, and I like number theory problems, and also, it was mostly we were trying to figure out what to do for this, for G4G.
Thank you, Gabe, and thanks again to all of our great speakers.